The Focus Applied Technologies Power Strecher can be easily integrated into any fuel injection system. It really just needs to measure from a few things. Your throttle body controls the injector. It also reads from the O2 sensor. The connection for the injector is very important. The injector has two wires on it, a live 12-volt line, and then the injector driver line. We need to intercept the injector driver line between the ECU and the injector. It's driven into the power stretcher via the injector sense line, and then we have the injector driver line. Usually that's the thicker of the two wires of the same color. Additionally, we want to read the throttle position. So your throttle position sensor generally has three lines. There's a 5-volt reference line and a signal ground, and then there's the TPS signal. Usually that's from about maybe a half a volt to 4.5 volts, somewhere in that region, and it changes as you open and close the throttle. We tap that line and read it into the power stretcher as the throttle position. That is used to control which bin of fueling or stretch we use. Additionally, the third sensor we have is the O2 sensor, the oxygen sensor. The oxygen sensor also generally has a ground line and then the signal line. The oxygen signal, when the vehicle is running in O2 control, it generally oscillates slowly between 0 and 1 volt. Now, we need to read the oxygen sensor and send out a synthetic oxygen signal to the stock ECU. The reason is you can add as much fuel as you want via stretching the injection pulse width. But if your ECU, the stock ECU, is still paying attention to the O2 sensor, it will eventually remove all your additional fuel. That's because it's using the O2 sensor as a closed-loop control system for the air-fuel ratio. Thus, it's very important that we not only control the injector, but we also control the O2 signal that's going back to the stock ECU. One more thing that's very important to see here is there are actually two different ground lines. There's the power ground, which is a big fat black wire, and there's a signal ground. Now, the signal ground, that's the same as the ground going to the throttle position sensor, and usually the O2 sensors and other temperature sensors and whatnot. The signal ground and the power ground are not the same, even inside the standard ECU. The signal ground is very quiet, there's no electronic noise on it, and it isn't demanded to sink any high currents or something like that. The power ground is usually a fat wire going directly to the frame or the battery's negative terminal. On our power stretcher controller, it's the same way. We have a power ground, and that's where we short the injector driver line through when the injector's turned on. We also have a signal ground, and that must be connected to a quiet ground or a signal ground from the standard ECU. Generally, we take the ground line from the throttle body. That's nice and quiet. If you combine these two together, generally you'll wind up with a lot of noise getting into the controller and erratic signals, something like that. Now let's go see about calibration. Now we want to look at the electrical connections and how you can find out the right signals for the power stretcher. What we've got on our right-hand side over here is a small electronic fuel injection setup. We use this a lot for demonstrations. So one of the first signals we want to look at is the throttle position signal. And remember, we mentioned that that goes from about a half a volt to about 4.5 volts. So here's our throttle position sensor. As I open and close it, you can see that the signal is going from, in this case, about 0.6 volts up to maybe 4.8 volts, something like that. So we know that this is the throttle position sensor. Also, we want to look at and identify the O2 signal. In this case, we don't actually have a running engine, so we simply tapped the O2 line here. We have a fake one I have to actuate with buttons. But when it goes high, you see it goes up to about a volt, and when it goes low, it goes down to about 0. So that's our O2 signal. Now on the injector, again, it has two wires. One which is hot full-time, that's 12 volts. The other one which is run to ground via the controller. Lastly, we want to run the power to the unit. You can see if you pull the cover off of it when it has power, you can see that it's got a blinking light. And remember, there are two grounds. We want the fat ground to go to a frame ground or something like that. And the thin wire is the signal ground, and that would be a ground something like you would put on the TPS, the throttle position sensor. Okay, once you have the unit powered up, you can connect it to a computer, either via serial cable or maybe something like Bluetooth. Now that we've got it up and running, let's confirm that it's actually reading. Generally, you can see numbers shifting down here at the bottom of the screen. We've connected to the TPS but haven't calibrated it, so I should be able to raise and lower my TPS, and you can see the TPS is reading, and it's going from negative something to over 100% because it hasn't been calibrated. Anytime it's out of a normal range, it will go red, and that's an indication that it needs calibration. Additionally, we can see that we're reading from the oxygen signal, oxygen sensor 1. This is a 2-cylinder version, but we're only listening to one sensor right now. If we spin up the engine, click that on, what you'll see is we'll have an RPM reading. Now, on this particular engine, the simulator, it idles at about 1,300 RPM. You can see that our reading here is about 2,600 RPM, so we need to click on the RPM key here to change the calibration factor. We click on it once, and we've got the appropriate factor. If you've got a different engine configuration, you may have to click on it a second or a third time. If you forget, you can just go back to the first position and then click it down until you've got the appropriate speed. Okay, we know we have the right speed now, and we can read the TPS and O2, so basically we're ready for calibration. Let's start by calibrating the throttle. You can calibrate it manually via this manual calibration over here, where you set up each one of the individual throttle bins, but it's actually much easier to throttle automatically calibrate it. If you hit the Throttle Auto Cal, it'll calibrate it in about 5 seconds. What you do is you click on it, you go wide open throttle, you go close throttle, and basically that's it. It's in cal mode, now it's finished, and what it's done is it's rescaled our throttle to go from 0% to 100%. So right now, my throttle's closed, I'm at 0%. As I open it, there's 50%, et cetera, and it goes all the way up to wide open throttle. In this case, just slightly over 100, 101%. That actually doesn't matter. Okay, so we've got the TPS cal'd. The next important thing to calibrate is the O2 setup. Now, there's 3 different modes you can see in O2. It starts up in map mode. It goes to a position where it's off. It's not actually controlling the O2. It basically follows it. Or shift mode. Shift mode is certainly the easiest mode, the safest mode to use. But let's look at the calibrations for it. Click on the O2 setup, and you'll get this screen. And there are several different things on the screen to look at. So the 2 major modes of control we have are the shift mode, and it's very easy to use. Basically, you just type a number in here. If your number is 100, then you're not applying any shift. What that means is the O2 signal sent to the ECU will always be the same as the O2 signal from the sensor. If we make it a little bit higher than 100, what that does is it will bias the running of the engine rich, so you'll get a little bit more fuel based on just the O2 sensor. If we give it a number less than 100, let's say 90, what happens is that will cause the standard ECU to bias the engine lean. So normally if you want to run rich, you'd set this number to say 105 or 110, something like that. The maximum is 120. So that's the shift mode. If we're using the map mode, down here you've got a map, and this is a map of your duty cycle. Remember, the O2 goes rich, lean, and normally it has about a 50% duty cycle. So at the lower throttle settings, that's usually the number we use, 50%. As you go to higher throttle settings, actually wide open throttle, it usually goes to 100% duty cycle. That means it's rich full time. So maybe a typical map might look something like this, where when you get to about 80%, you'd say, well, we'll have a 75% duty cycle, something like that. The duty cycle gets higher the higher you go in your throttle. Additionally, we have a range here of throttle positions. Below a certain throttle position, usually we set it for about 5%, your O2 signal will actually follow the real sensor. There's a good reason for that. It allows the O2 compensation to re-zero itself at idle. Also, it gives very good idle performance. Typically, we also want the O2 sensor, the O2 signal sent to the stock ECU to follow the real sensor above something like 80%. The reason for that is when you go wide open throttle, your stock ECU will run rich. Well, we want to be able to listen to the O2 sensor. In case there's any problem with it, it should show up that there's a problem, and it will flag the malfunction indicator light. So if you do this, what happens is above 80%, you'll actually listen to the real O2 signal, even when you're in this map mode. There are some other parameters down here. Generally, you don't need to play with those. You can adjust the switch voltage a little bit. If you want to bias rich again, you can maybe make this number a little bit higher. Instead of, say, 0.5, you could make it 0.6, and that will tend to bias you a little bit richer. When you're happy with those, you simply click OK, and now they're saved. So we should be able to see that we're in map mode, and right now we are following, because we're at idle, we should be following the O2 signal. So every time I hit the rich button, you can see both the real and the synthetic, the real meaning from your sensor and the synthetic sent to your ECU, both of those go rich, that's green. When I hit the lean button, they both go red. So rich, lean, and it follows it. Now if I open more than 5% on my throttle, we can see the synthetic signal being sent to the ECU says it's rich, lean in a 50% duty cycle. When I get closer to 80%, now it'll go to a 75% duty cycle, right about there, and you can see it's rich most of the time and lean for only a short period of time. And if I go above 80%, now it follows the real signal. Now at above 80%, the thing will always run rich, and so you'd expect to see something like this. As I decrease the throttle, now it's running in synthetic mode, so although the engine is actually rich, we're telling the ECU it's not rich, it's roughly stoichiometric. So that's the beauty of the map mode. Of course, the other mode is shift. Let's try shift mode. So this is off, so now we're always following the real signal. You see rich, lean. If we go to shift mode, what happens is every time I go rich, so the real sensor went rich, the synthetic sensor, the synthetic signal goes rich, but only after a certain while. When they go lean together. Now I'm going to go rich now, and so it goes rich, and then after some delay, the signal going to the ECU goes rich. When they go lean together. So rich, okay, and then lean together. So that's what the shift mode is, and that causes the stock ECU to run a little bit richer. Okay, now we have the O2 setup calibrated, we have the TPS calibrated, and essentially we can burn this to memory if we're happy with it, and then we can play around with the shift. Let's look now at how the stretch actually works. What we have is an oscilloscope here looking at the signal both from the actual injection driver and then the shifted, the stretched injection driver signal, and then our standard software interface. So we'll turn the engine on. And we can see that we're reading the injection signals. This is from the driven line, so it goes low when the injector's on. And you can see that we've got our RPM reading down here, and as I actuate the throttle, we've got the throttle reading. We also have our O2 reading online, but I'm not playing with O2 right now. So one of the first things to notice is that our stretch is actually a function of throttle. Down here we have the various throttle bins, and you can see which bin is being highlighted depends on the throttle. So here we're at about 80% throttle, so that bin is highlighted. Go to full throttle, and now the wide open throttle is highlighted. So as we go down in throttle, we highlight the bins to the left, and as we go up in throttle, highlights the bins to the right. Now the number on the top is the actual stretch. So for example, at idle, maybe I don't want to have any stretch, so I'm at 100%. And you can see both the incoming injection signal and the outgoing injection signal are the same size. Now, in this case, I've revved it up to about 20%, and I've just a little bit of stretch. So this is my stretched pulse width. This is the standard pulse width. The stretched pulse width is a little bit bigger. You can't really see it because it's only about a 2% stretch. But let me increase that. To increase it, I can go and click on this arrow, and that'll give me 0.5% increments. Or I can click just below it, and that'll give me 5% increments. So now it's very clear. I have quite a big stretch, about 30% stretch. If I go back down and throttle, the pulse width goes to the normal pulse width. So at idle, it's running exactly how it should, and in fact, it'll be in O2 control. So as O2 goes rich and lean, it will reflect that in the actual signal. Now we're in shift mode. Let me go to map mode. So we'll go to map mode, and what you see in map mode is that the two signals are exactly the same. They go rich and lean together when we're at idle. When we rev up beyond about 5%, now we're stretching the signal, but the signal going to the stock ECU says it's going rich, lean, rich, lean. In reality, it would look something like this. We'd be rich full time because we've stretched the pulse width, but the stock ECU is going to think that it's stoichiometric because the synthetic signal is oscillating rich lean, rich lean. Also, when we go wide open throttle, once again, we should see that the system goes rich and we're following. We're no longer oscillating, and this is good so that the ECU can tell, okay, my sensor really is working and we really are rich. So essentially that's it. What you do is you set up your stretch. When you're happy with it, you burn it to memory. There's 3 different maps you can use. And also, if, for example, you want to shut the stretch off, you just click on stretch and shut it off. Now we're not applying any stretch at all, so our stretch is 100%. So the outgoing signal and incoming signal will look exactly the same, in case you need to do emissions testing or something like that, or normal driving. When it's race day and you want to race, okay, you turn your stretch back on and now you're stretched. Or maybe you have a mild map for map 1 and a radical map for map 2, etc., etc. Okay, all that's left now is to see how it performs on an actual vehicle. We're looking at a twin-cylinder 250cc fuel-injected motorbike, Posian, sold in Malaysia as a NASA. And what we're going to do is we're going to rev it up on the dyno and road load mode. And then what we'll do is we'll turn on the O2 control, turn on the stretch, and what you'll see is every time the stretch goes on, the power goes up because we're giving it significantly more fuel. You'll also see that the O2 will be switching initially, and you also can notice it as a Delphi. Okay, roll it up. It's actually a little lean. I'm going to turn on the synthetic O2 and I'm going to turn on the stretch, and you can hear it revs up quite a bit. If I shut the stretch off, it goes down. Every time I turn on the stretch, it actually goes rich and it revs up quite a bit. When I shut it off, it slows back down again. That's because we're putting in extra fuel.